So in this chapter, we're going to be talking about stoichiometry, and we're almost done all of the material for this class, if you can believe it. But before we get into what we mean by stoichiometry, we want to talk about conversion factors from chemical equations. And we've seen this example before where we have hydrogen reacting with oxygen to form water. And when we learned about balancing chemical equations, one of the things that I mentioned in passing is that the coefficients in a balanced chemical equation give us the conversion factors to convert from the number of particles of one substance expressed in moles to the number of particles in another substance expressed in moles during these chemical changes. So for example, we have these coefficients here in this balanced chemical reaction. And how I can interpret this is that 2 moles of hydrogen react with 1 mole of oxygen to give us 2 moles of water. So again, these coefficients tell us the number of moles we have for this balanced chemical equation, and we can use that to convert between moles of one substance to moles of another substance, okay? So this gives us our conversion factor. So it's a ratio, okay? So that's what we have here. So this mole ratio between 2 species, right, that comes from a balanced chemical equation gives us a per expression that we learned about in our chapters way back in chapter 3 on dimensional analysis. So again, remember I said that it's really important we know that chapter and understand it because we're going to be using that information throughout the semester. And here, the problems we're going to be doing are a little more complicated than converting feet to inches, but that doesn't mean they're hard in this chapter. It just means that we have to understand a little bit better on how to do dimensional analysis. So if you're having trouble with that chapter, I suggest you go back and watch a few of those videos and refresh yourself on dimensional analysis. But these coefficients here give us a ratio or a per expression that we can convert from moles of a given species to moles of a wanted species. For example, there's 2 moles of hydrogen for every 1 mole of oxygen. That's something I already said. So just like there's 12 days, or 12 days, what am I talking about? Just like there's 7 days in a week. I don't know where 12 days came from. Maybe that's on somebody else's calendar, but just like there's 7 days in a week, right? In this case, there's 2 hydrogens for every 1 oxygen, okay? It's a conversion factor. So that's how we can go from moles of one substance to moles of another substance. Okay, so again, we can think about it this way. If we had a hamburger here, or a cheeseburger, I guess it is, and we wanted to make it, okay, let's say you worked at McDonald's, or maybe you do work at McDonald's, and you're making a Big Mac or whatever. Well, I guess it'd be different for Big Mac. There's different amounts of buns. Anyway, in this case, we want to make this guy. So you have 1 hamburger bun, okay, 1 hamburger patty, 1 slice of cheese, 1 piece of lettuce, 2 slices of tomatoes. You put all those together in this reaction and you get 1 cheeseburger, okay? That's what we end up with. So again, these coefficients, right? 1, 1, 1, 1, 1, or 2, and then 1, again, tell us, right, how we can convert from one thing to another and understand these relationships. It's the same with chemical equations, as we'll see in a second. For example, you might be asked questions like this, of course, for chemical reactions, but if I have 5 cheeseburgers, you know, how many hamburger buns did I use? Well, you use 5 because it's a 1-to-1, in this case, relationship. How many patties did you use? Again, you use 5. How many slices of tomatoes did you use? Well, in that case, you're going to use 10 because there's 2 slices of tomato per cheeseburger and you made 5 of them, right? So this is a simple example to kind of give you the idea of what we mean by kind of using these coefficients to convert between moles of one thing to moles of another thing. It's the same concept as with this cheeseburger. So let's do an example then so it can become more clear. How many moles of oxygen are needed to completely react with 2.34 moles of ammonia in a reaction that yields nitrogen monoxide and water? So in this case, we're given the reaction, That's not always going to be the case. And when we're not given the reaction, as we're going to see, we're going to have to use our knowledge on how to write down chemical reactions properly in order to do these problems. So let's see here. Again, we're going to use dimensional analysis. So what we should do is write down what's given. Okay, so we're given 2.34 moles of NH3, okay? And I want moles of oxygen, okay? And from then, if I want to convert here, I can look at for my per expression or my ratio or conversion factor, however you want to think about it, it comes from here. So I know that there are 5 moles of oxygen for every 4 moles of ammonia. Okay, so that's the way I'm going to convert between one thing and another. So I'm going to start with what's given, right? 2.34 moles NH3. Okay, and then my conversion factor, okay, here and here, okay, for every 4 moles NH3, ammonia, there's 5 moles of oxygen, okay? So if you put that in your calculator, I got 2.93 moles of oxygen. Remember, significant figures still matter here, but the for exact numbers, okay, they have an infinite amount of significant figures, so you don't look to those. So the 5 and the 4, we're not going to round this to one significant figure. In other words, ignore the 5 and the 4 here. They don't count as only having one significant figure. They're exact numbers, so they have infinite amount of significant figures, if you remember those rules. And again, if you don't, go back to chapter 3 and review that a little bit. So I'm just plugging in my calculator again. Yep, and this is what I get. Okay, so again, this is how we're going to do these types of problems. Let's do a few more examples that are maybe a little bit tougher because we're going to have to balance the chemical equations here. So in this example, it says how many moles of oxygen are required to burn 2.4 moles of ethane. Okay, so actually what I want you to do is pause the video, try to write down the chemical equation. It's a combustion reaction. Write down the equation and balance it, and then try to do the problem on your own. Okay, so the balanced chemical equation for this, I'm just going to write it down because we had plenty of examples balancing chemical equations in our quizzes and labs and all sorts of things. So in the homework, so I'm assuming we're pretty familiar with this step. I want to kind of get past that in this video and talk more about these conversion factors. But if you have trouble, go back and watch those other videos. Okay, so this is the balanced chemical equation. And again, we're given 2.40 moles of ethane. And I want moles of oxygen. Okay, so again, I'll just change color here. Write down using some dimensional analysis. H6 times, okay, for every 2 moles, in this case, of C2H6, okay, there are 7 moles of oxygen. And this is something I didn't mention in the last slide, but notice that the units of moles here, in this case of ethane, cancel with the unit moles of ethane, so that I'm left with moles of oxygen. So you should always check to make sure that your units cancel properly and that you're left with what you want, okay? So with all of that, I get 8.40 moles of oxygen, okay? Pretty easy. Again, this is converting between moles of one thing to moles of another thing. I'm just gonna plug that in my calculator one more time. Yep, and that's what I got. Okay, so here we go. Let's do another example. So this is an example of a combination reaction or a synthesis reaction. So again, we're going to need to know those reactions and be able to interpret these problems and balance the equation. So it says ammonia is formed directly from its elements. How many moles of hydrogen are needed to produce 4.2 moles of ammonia? So again, why don't you pause the video, try to do this one in your own, and then we'll do it together. Okay, well, going a little bit faster now, I'm just going to write down this equation. Okay, so that's my equation right here. I am given 4.20 moles of NH3. I want moles of hydrogen. Okay, so now 4.20 moles of NH3 times, well, for every 2 moles of NH3, there's 3 moles of hydrogen. Okay, so when I put that in my calculator, I get 6.30 moles oh my goodness, nope, wrong. Moles of hydrogen, sorry. Right, because the units of moles NH3 or moles of ammonia canceled out, and I'm left with moles of hydrogen. So again, check your units. Don't be like me. All right, so I think that's it. Yep, for this section. And in the next video, we're going to be building on this and talking about how we can convert from grams of one substance to grams of another substance. So I'll see you there.